H1821+643 is an extraordinary celestial object, known for being one of the rarest and most luminous quasars situated within a massive galaxy cluster. Located approximately 3.4 billion light-years away from Earth in the constellation Draco, this quasar resides at the very heart of a gigantic elliptical galaxy, embedded within a densely populated cluster of galaxies. Quasars, or quasi-stellar objects, are incredibly bright, energetic nuclei of distant galaxies, powered by supermassive black holes that vigorously accrete vast amounts of matter. What distinguishes this remarkable quasar from most others is not merely its intrinsic brightness, outshining many objects in the observable universe, but also its peculiar placement within a rich cluster environment. Typically, quasars are relatively isolated or situated in less dense cosmic surroundings, making this one's location particularly significant. Such an exceptional setting allows astronomers to study interactions between powerful energetic emissions and the surrounding intracluster medium, shedding light on galaxy evolution and the dynamic interplay between supermassive black holes and their host galaxies. At the core of the system lies an extraordinarily massive black hole, estimated at around 30 billion solar masses, placing it among the most massive ever discovered. This immense gravitational engine actively feeds on gas and dust swirling around it, generating an accretion disk that radiates energy across the electromagnetic spectrum, from radio waves to X-rays. Observations with NASA's Chandra X-ray Observatory have offered crucial insights, revealing an extended halo of hot, X-ray emitting gas enveloping the central galaxy and reaching far into the surrounding cluster. This expansive halo has proven invaluable for astrophysicists investigating feedback processes, phenomena through which energy from black holes regulate star formation. Such mechanisms can either trigger or suppress stellar birth by heating and dispersing gas clouds. In this particular case, intense X-ray emissions and powerful relativistic jets, launched from the vicinity of the black hole, significantly impact the intracluster medium, potentially affecting star formation rates across the entire cluster. Moreover, the presence of such a luminous quasar within a dense galactic environment provides a unique laboratory for gravitational lensing studies. The immense gravitational fields of the surrounding cluster bend and amplify the emitted light, producing lensing effects that allow astronomers to map dark matter distributions and gain deeper insight into the universe's large-scale structure and the elusive nature of dark matter. The distinctiveness of this cosmic beacon is further underscored by its rarity. Despite extensive sky surveys conducted by numerous observatories and space telescopes, very few quasars of comparable brightness and mass have been found in similarly dense environments. Each new observation and theoretical analysis contributes to our understanding of cosmic evolution, particularly regarding the growth of supermassive black holes and their influence on galactic ecosystems. Ongoing studies utilizing advanced instruments such as the Hubble Space Telescope and the Very Large Telescope, VLT, as well as planned observations with next-generation facilities like the James Webb Space Telescope, JWST, promise even more precise characterizations. These future missions aim to delve deeper into the physics of accretion, the role of quasars in galaxy formation, and their long-term effects on the cosmic environment. Ultimately, this rare object stands as a cornerstone of modern astrophysical research, offering a glimpse into extreme gravitational, energetic, and cosmological phenomena that continue to shape the universe. Its unique location within a massive galaxy cluster, exceptional luminosity, and astonishing central black hole make it one of the most valuable targets for current and future exploration in cosmology, astrophysics, and the fundamental study of black holes. This extraordinary and exceptionally rare quasar occupies a unique position at the heart of a massive galaxy cluster. Located approximately 3.4 billion light-years from Earth in the direction of Draco, it has drawn immense scientific interest due to its remarkable luminosity, extraordinary mass, and unusual location within a richly populated galactic environment. While such objects, extremely bright, active galactic nuclei powered by supermassive black holes, are not uncommon, the vast majority tend to reside in isolation or in sparsely populated regions of space. That makes this case especially compelling, as it exists in one of the densest cosmic settings known for such phenomena. At its core lies an ultramassive black hole, estimated to be around 30 billion times the mass of the Sun, among the most massive ever recorded. This gravitational colossus actively pulls in enormous quantities of matter, including gas, dust, and even stars from its surroundings. The infalling material forms an extremely luminous accretion disk, a turbulent swirl of superheated matter spiraling toward the event horizon. As the material heats through friction and gravitational compression, it radiates intensely across the entire electromagnetic spectrum, from radio waves and infrared, to ultraviolet and X-rays. The result is a cosmic beacon visible across immense cosmological distances. Observations using NASA's Chandra X-ray Observatory, the Hubble Space Telescope, the Spitzer Space Telescope, and ground-based facilities like the Very Large Telescope, VLT, have revealed remarkable details about the object's physical processes and cosmic context. Notably, X-ray data show an extended halo of hot gas surrounding the host galaxy, stretching hundreds of thousands of light-years into the cluster environment. This envelope, heated to tens of millions of degrees, serves as a vivid example of how powerful quasars can shape their surroundings. The significance of this system extends well beyond its brightness and central black hole. Its residence in a dense cluster offers a rare chance to study the complex dynamics that arise when energetic outflows from active galactic nuclei interact with the intracluster medium, a vast reservoir of hot, diffuse gas filling the space between galaxies. As the largest gravitationally bound structures in the universe, galaxy clusters provide a unique environment for such feedback mechanisms. By examining how this quasar interacts with its surroundings, scientists gain insights into how black holes influence the rate of star formation, redistribute intergalactic gas, and drive the thermal evolution of entire clusters. One especially compelling aspect of this interaction is the phenomenon of feedback. Here, outflows, relativistic jets or intense radiation, can heat and expel the gas needed for star formation. This process can suppress stellar birth within the host galaxy and neighboring systems. In this case, the immense gravitational energy released by accretion fuels powerful jets that extend thousands of light-years, inflating cavities, producing shock waves, and stirring turbulence throughout the surrounding cluster. These interactions can significantly alter the efficiency of star formation on massive scales. In addition to feedback, the object serves as a powerful tool for studying gravitational lensing. The tremendous gravitational field of the surrounding cluster bends and amplifies light, distorting the view of more distant background objects. The quasar's light, affected by these distortions, allows astronomers to trace the invisible structure of dark matter within the cluster. Since dark matter cannot be observed directly, gravitational lensing remains one of the most effective tools for understanding its distribution and role in cosmic evolution. Beyond the dark matter lensing studies, this system also provides crucial information about how supermassive black holes grow. Current theories suggest that the most massive among them acquire their mass through extended episodes of rapid accretion, often triggered by galactic mergers. Studying such a powerful quasar in a dense environment helps researchers understand whether growth processes differ depending on the surroundings, and what that means for the formation of early galaxies and black holes in the universe. Future missions promise to bring even deeper understanding. Instruments like the James Webb Space Telescope, JWST, the European Extremely Large Telescope, EELT, and the Square Kilometre Array, SK, will dramatically improve resolution, sensitivity, and wavelength coverage. With them, scientists will explore how energy from quasars shapes galaxies and clusters, test new models of feedback, and refine maps of dark matter with unprecedented detail. Ultimately, this quasar represents a convergence of extremes, record-breaking luminosity, an enormous black hole, and a rare location in the heart of a massive cluster. It stands as a vital touchstone for probing some of the most complex processes in the cosmos, from black hole growth and star formation regulation, to gravitational lensing and dark matter mapping. Continued study will not only advance astrophysics and cosmology, but also deepen our broader understanding of the structure and evolution of the universe itself. Indeed, the study of this remarkable quasar continues to illuminate a multitude of interrelated cosmic mysteries, with each deeper exploration offering fresh insights into the fundamental physics that govern the universe. Thanks to its extraordinary luminosity, the object is easily detectable across vast cosmological distances, making it a critical benchmark for investigating cosmic evolution, particularly the formation of large-scale structures throughout cosmic history. Since quasars serve as distant beacons visible through billions of years of cosmic expansion, precise measurements of their light and emissions, exemplified in this case, help refine our understanding of essential cosmological parameters such as the rate of expansion, the behavior of dark energy, and the universe's overall geometry. Astrophysicists are especially intrigued by the detailed spectral signatures emitted by this system, which offer critical clues about the extreme conditions near the black hole's event horizon and the dynamics of accretion under intense gravitational fields. High-resolution spectroscopy across the electromagnetic spectrum, from radio to ultraviolet and X-rays, has enabled researchers to dissect its emission lines and identify specific atomic transitions in ionized gases surrounding the central engine. These spectral fingerprints allow scientists to determine the velocity, temperature, and density of the accretion disk and its surrounding gas clouds, while also probing the structure and composition of energetic jets and winds. Such studies are essential for testing general relativity near strong gravity fields and refining theoretical models of accretion physics, jet dynamics, and black hole energetics. This luminous quasar also serves as a natural laboratory for examining the interaction between powerful jets and magnetic fields within galaxy clusters. The massive relativistic jets, launched through rotational and gravitational energy extraction from the central black hole, are thought to play a pivotal role in magnetizing the intracluster medium. As these jets propagate through surrounding plasma, they shape the strength and orientation of magnetic fields that permeate the cluster. These fields, in turn, influence thermal conduction, turbulence, and the distribution of cosmic rays. Understanding the magnetization process, facilitated by such energetic outputs, provides essential insights into the formation and evolution of cosmic magnetism across large-scale structures. Moreover, the extensive dataset available for this source has implications that extend into particle astrophysics and high-energy neutrino research. As one of the brightest known quasars, it is a candidate source for high-energy neutrinos. The vicinity of highly active supermassive black holes is believed to be capable of accelerating particles to extreme energies, where interactions between protons and intense radiation fields may produce neutrinos. Facilities such as IceCube, Antares, and future neutrino telescopes continue searching for such signatures. Confirming the emission of high-energy neutrinos from sources like this one would significantly advance our understanding of cosmic accelerators and their role in the high-energy universe. In addition to neutrino astronomy, this quasar presents exciting prospects in gravitational wave astrophysics. Although current detectors like LIGO and Virgo are not sensitive to gravitational waves produced by individual supermassive black holes, future space-based missions such as the Laser Interferometer Space Antenna, LISA, are designed to detect signals from mergers involving such titanic objects. Considering its immense scale and clustered environment, it's plausible that this system formed as a result of previous galaxy mergers, potentially leaving gravitational wave signatures detectable by future observatories. Detecting such waves would provide direct information about the growth history and merger activity of massive black holes in dense environments. The rarity of objects like this underscores the importance of systematic sky surveys in uncovering more examples in similar cosmic settings. Upcoming observational efforts, including the Sloan Digital Sky Survey, SDSSV, the Legacy Survey of Space and Time, LSST, conducted by the Vera C. Rubin Observatory, and missions involving the Nancy Grace Roman Space Telescope, are expected to expand our catalog of extreme quasars. By identifying more sources of similar brightness and environmental complexity, astronomers can place unique cases like this one into a broader statistical and evolutionary framework. Beyond purely physical studies, this quasar also has implications for astrobiology and the potential habitability of galaxies in clusters. While such active nuclei emit intense radiation capable of sterilizing nearby regions and halting star formation, they may also stimulate stellar birth in more distant clouds through shock compression. As a result, research into this object helps explore the dual role of quasars, as both destructive forces and catalysts of creation, in shaping the evolutionary and habitability potential of galaxies in dense environments. Ultimately, this luminous and rare system stands as a cornerstone of modern astrophysical inquiry. It challenges theoretical models and inspires new questions across multiple domains, from gravitational physics and cosmic magnetism to high-energy particles, galaxy evolution, and cosmology. Continued and expanded investigations of this quasar will undoubtedly yield transformative discoveries, pushing the boundaries of knowledge and deepening our understanding of the universe's most extreme and awe-inspiring phenomena. Moreover, the extensive research potential of this extraordinary quasar extends into the rapidly evolving field of computational astrophysics and numerical modeling. Advanced simulations have become indispensable for deciphering the complexities of quasar behavior, black hole growth, and galaxy cluster dynamics. In this context, precise observational data from the system can be integrated with cutting-edge hydrodynamic, magnetohydrodynamic (MHD), and particle-in-cell (PIC) methods to construct highly detailed models of its environment. These simulations offer crucial insights into how such luminous active nuclei shape the intracluster medium, influence nearby galaxy evolution, and modify the thermodynamic state of the intergalactic gas. High-resolution models also help astrophysicists unravel turbulent processes, shockwave propagation, and intricate magnetic field geometries created by powerful jets and radiation pressure. In particular, simulations can replicate the feedback cycle, wherein energetic jets heat and displace large volumes of gas, altering the cluster structure, either quenching star formation or triggering it through compression in distant gas clouds. This level of modeling is essential for validating theoretical frameworks concerning feedback, magnetization, and the long-term coupling between black holes and their environments. On the observational front, upcoming advances in radio astronomy are especially promising for further investigations of this system and others like it. The Square Kilometre Array, SKA, poised to become the world's most sensitive radio telescope, will greatly enhance our ability to study radio emissions and relativistic jets with unprecedented clarity. These observations will illuminate jet structures, propagation dynamics, and interactions with surrounding plasma. In particular, polarization studies and analyses of synchrotron radiation will deepen our understanding of magnetic field evolution within galaxy clusters and clarify how energy and magnetic flux are distributed on large cosmic scales. Precision cosmology also stands to benefit from continued exploration of luminous quasars like this one. Accurate measurements of redshift, luminosity, and spectral features contribute to improved distance calibrations, essential for resolving discrepancies such as the current tension in the Hubble constant. Because of their brightness and consistency, quasars are being explored as quasi-standard candles, providing independent cross-checks on cosmic distance ladders. The stability and power of this quasar's emission spectrum help anchor such efforts and refine our models of universal expansion, dark energy, and large-scale structure. In addition, the object's sheer luminosity across multiple wavelengths makes it an ideal probe of the intergalactic medium, IGM. Absorption lines visible in its spectrum allow astronomers to study the composition, temperature, ionization, and density of matter in intervening galaxies and cosmic filaments. These observations trace the large-scale structure of baryonic matter and provide insights into the baryon cycle, how gas flows into and out of galaxies, shaping their star formation and long-term evolution. Another exciting frontier involves temporal variability studies. Quasars often vary in brightness and spectral output over time, reflecting dynamic changes in accretion disks and jet activity. Long-term monitoring of this particular object, through both ground-based and space-based observatories, could reveal patterns of variability that shed light on internal processes like magnetic instabilities, jet precession, and disk-jet coupling. These changes serve as real-time tests of theoretical models concerning black hole spin, matter inflow, and relativistic outflows. At the intersection of astrophysics and fundamental physics, this quasar also provides a valuable testing ground for alternative theories of gravity. Given the system's extreme mass and deep gravitational potential, it offers rare opportunities to observe high-curvature spacetime effects that could hint at deviations from general relativity. Precision measurements of jet trajectories, lensing distortions, and photon paths near the event horizon may one day help constrain or confirm extensions to Einstein's framework. From a science communication perspective, this quasar also holds exceptional value. As a vivid example of cosmic extremes, bright, massive, and active, it naturally captures public interest in black holes, galaxies, and the universe itself. Stunning imagery and engaging narratives surrounding this object make it ideal for educational initiatives, museum exhibitions, and planetarium programs aimed at inspiring interest in astronomy and STEM education. In sum, continued investigation of this luminous cosmic powerhouse offers transformative potential across multiple domains of science. Its rarity, brightness, and environmental complexity provide a uniquely rich framework for advancing our knowledge of black holes, galaxy formation, high-energy physics, cosmological evolution, and gravitational theory. Each new observation or simulation contributes to a more complete portrait of how the universe works on its largest and most extreme scales. More than just a quasar, it stands as a dynamic symbol of humankind's quest to comprehend the deepest laws of nature. As the quest to understand this remarkable quasar intensifies, it increasingly influences interdisciplinary research at the forefront of modern astrophysics, cosmology, and fundamental physics. Its study fosters collaborations across observational astronomy, theoretical physics, computational science, and particle astrophysics, uniting diverse scientific communities in the shared pursuit of unraveling its profound mysteries. These integrated approaches have given rise to innovative techniques, from enhanced data analysis algorithms to advanced simulations replicating the extreme environments around supermassive black holes and galaxy clusters. One particularly promising direction is the integration of data science and machine learning. State-of-the-art AI techniques, such as deep learning and neural networks, now enable the efficient analysis of massive observational datasets. These tools can detect subtle spectral patterns, track previously unnoticed luminosity variations, and rapidly classify complex multi-wavelength signatures suggestive of jet interactions or gravitational lensing. Applying artificial intelligence to systems like this accelerates discovery, increases predictive precision, and deepens our grasp of phenomena at the frontier of observability. Its environment also provides a unique opportunity to investigate cosmic metallicity, the abundance of heavy elements in the universe. By examining emission lines from the ionized gas surrounding the quasar, astronomers can reconstruct the enrichment history of elements like carbon, oxygen, and iron, tracers of earlier stellar generations. These measurements illuminate the chemical evolution of galaxy clusters, revealing how star formation and nucleosynthesis have shaped the composition of the universe over billions of years. The powerful feedback effects observed in and around this object offer crucial tests for galaxy formation models and cosmological simulations. Modern large-scale structure models rely on AGN feedback to match observed galaxy distributions and evolution. With its exceptional brightness and measurable impact on the intracluster medium, this quasar serves as a critical real-world benchmark. Comparing observational data with simulation outputs allows researchers to calibrate parameters more accurately, improving predictions on how galaxies and black holes co-evolve, and how matter, both baryonic and dark, is distributed on cosmic scales. In the realm of particle physics, the extreme energy densities and relativistic conditions near the central black hole offer a natural laboratory for high-energy phenomena beyond the reach of terrestrial experiments. Observing particle acceleration in jets near light speed opens pathways to studying relativistic plasmas and quantum electrodynamics in extreme regimes. These insights feed directly into cosmic ray research and high-energy astrophysics, and may even point toward new physics beyond the standard model. The object's staggering mass and energy output also intersect with theoretical investigations into quantum gravity. Massive black holes like this one offer fertile ground for testing concepts such as holographic principles, black hole entropy, and quantum spacetime geometry. Some theorists speculate that subtle deviations in accretion behavior, jet dynamics, or photon paths might reveal indirect imprints of quantum gravity effects, making such luminous quasars valuable probes of the deep interface between general relativity and quantum mechanics. From a technological perspective, the challenge of studying extreme environments like this has motivated significant advances in telescope design and astronomical instrumentation. Cutting-edge observatories, such as the James Webb Space Telescope, the Extremely Large Telescope, ESA's Athena X-ray mission, and the Space-Based Gravitational Wave Observatory LISA, have all been shaped in part by scientific goals centered on active galactic nuclei and galaxy clusters. The pursuit of knowledge about systems like this has driven progress in optics, sensors, spectroscopy, and interferometry, yielding benefits far beyond any single object of study. Beyond science, the quasar serves as a profound symbol of humanity's expanding cosmic awareness. Located billions of light-years away and observed as it appeared in the ancient universe, it reminds us of the vastness and interconnectedness of cosmic events. The forces shaping such colossal structures also help create the conditions for life-bearing worlds like Earth. In this sense, its study not only informs but inspires, deepening our philosophical and cultural understanding of our place in the cosmos. In summary, this luminous and rare system continues to enrich a broad spectrum of inquiry, spanning astrophysics, cosmology, fundamental physics, AI, and instrumentation. Each new discovery made through its study expands our scientific reach, challenges our theoretical frameworks, and fuels the timeless human desire to understand the universe. As investigations progress, this celestial giant remains both a beacon of knowledge and a powerful reminder of the mysteries still waiting to be unraveled. The insights gained from studying this exceptional quasar transcend purely scientific boundaries, influencing our broader understanding of the origin, structure, and fate of the universe. Its very existence within a dense galaxy cluster raises fundamental questions. How often do supermassive black holes attain such extraordinary masses and luminosities? Are such systems anomalies, or do they reflect deeper, yet undiscovered principles of cosmic evolution? Answering these questions could profoundly reshape existing cosmological models and our understanding of galaxy and cluster formation throughout cosmic history. This luminous quasar also plays a vital role in exploring the epoch of cosmic reionization. While it formed long after that transformative era, its immense brightness serves as an observational baseline for studying more distant quasars at higher redshifts. By doing so, astronomers gain insight into how powerful ultraviolet and X-ray sources contributed to the reionization of the intergalactic medium, a critical phase in the universe's transition from darkness to light. The complex interactions observed between this object and its intracluster medium allow astronomers to examine how galaxy clusters, some of the universe's largest gravitationally bound systems, assemble and evolve. Detailed measurements of gas temperature, density, and motion around the quasar offer clues about cluster mergers, turbulent heating, and dynamical processes that shape large-scale structure. These findings help refine models of dark matter behavior and the distribution of baryonic matter across the cosmic web. Future gravitational wave astronomy, especially with next-generation observatories like LISA, is poised to intersect meaningfully with the study of systems like this. Should such objects originate from supermassive black hole mergers, they may encode gravitational signals detectable in coming decades, offering direct insight into the history of galaxy and black hole assembly. On an experimental front, studying this system inspires new developments in laboratory astrophysics. Researchers are now reproducing aspects of its extreme environment in high-energy plasma experiments, simulating phenomena such as relativistic jets, accretion flows, and magnetic reconnection. This synergy between observation, theory, and experiment strengthens cross-disciplinary collaborations and brings cosmic-scale physics into controlled laboratory contexts. The environmental effects of quasar activity also impact the search for extraterrestrial life. While direct habitability near active quasars is unlikely, mapping how these giants influence their galactic neighborhoods helps define stability zones for star and planet formation. In this way, even objects as extreme as this contribute to refining astrobiological models and identifying promising regions in the cosmic web for future exploration. Pedagogically, this quasar offers students and researchers rich opportunities for hands-on learning in observation, simulation, and theoretical modeling. From accretion dynamics and feedback processes to gravitational lensing and chemical enrichment, the system embodies core astrophysical concepts that serve as ideal training grounds for the next generation of scientists. Culturally, it captures public imagination. Artistic visualizations of its jets, warped light paths, and luminous disks offer compelling material for education and outreach, inspiring wonder and curiosity in audiences beyond the scientific community. Through film, digital media, and planetarium exhibitions, it serves as both a scientific and philosophical symbol, reminding us of the vast, interconnected cosmos we inhabit. Looking ahead, the exploration of this cosmic powerhouse will be dramatically enhanced by next-generation observatories. Missions like Lynx, Athena, and JWST will probe accretion physics and feedback with unprecedented detail. Ground-based giants such as the 30-meter telescope and Giant Magellan telescope will dissect its galactic environment, while radio telescopes like SKA will map its jets and magnetic field interactions across intergalactic space. Ultraviolet and infrared missions like Origins will further unravel the dusty, molecular conditions feeding the central black hole. The quasar will also contribute to precision cosmology. Through effects like the Sunyaev-Zeldovich imprint on the cosmic microwave background, it enables detailed measurements of cluster mass and baryonic content, essential for constraining dark matter, dark energy, and the universe's expansion history. Time-domain astronomy offers yet another window. Long-term monitoring of variability in brightness and spectra will reveal clues about accretion instabilities, jet orientation shifts, and possible microlensing effects. These changes provide real-time insight into processes unfolding near the event horizon, deepening our understanding of black hole physics. In fundamental physics, such objects serve as laboratories for testing the limits of general relativity and probing possible quantum gravitational effects. Lensing observations, high-energy photon propagation, and jet dynamics may offer indirect clues about new physics, whether it be Lorentz invariance violations or quantum-scale spacetime curvature. Educationally, the quasar is a treasure trove. It vividly illustrates topics in gravitational theory, thermodynamics, high-energy astrophysics, and cosmic chemistry. As a teaching tool, it sparks curiosity and fosters critical thinking about some of the universe's most powerful phenomena. Philosophically, its immense age, distance, and scale invite reflection on humanity's place in the cosmos. It stands as a glowing reminder of the ancient forces shaping our universe, forces that gave rise not only to galaxies and stars, but ultimately to the conditions for life. In total, this extraordinary quasar bridges scientific disciplines and human perspectives. Whether refining simulations, calibrating cosmological models, testing particle theories, or inspiring a young mind, it remains a beacon of discovery. As astronomers continue to unlock its secrets, it will undoubtedly yield transformative insights into the structure, origin, and destiny of the cosmos, embodying humanity's relentless drive to understand the universe we call home. This rare and luminous quasar serves as a vital reference point for unraveling the coevolution of galaxies and their central supermassive black holes, a fundamental relationship that shapes the architecture of the universe. Observations consistently reveal strong links between a galaxy's stellar mass, morphology, and star formation activity, and the mass and behavior of the black hole at its center. By closely examining the interplay between this extraordinary quasar and its host galaxy, astronomers can better understand how feedback from active galactic nuclei regulates galactic growth, influences star formation, and guides the long-term evolution of entire galactic systems. On a deeper theoretical level, extreme cases like this challenge and refine current models of black hole formation. Cosmologists propose various pathways to explain the existence of ultramassive black holes, rapid accretion over cosmic time, mergers of smaller black holes during galaxy collisions, and even the presence of massive primordial seeds in the early universe. The central engine powering this quasar, with a mass reaching tens of billions of solar masses, presses theorists to reconsider how such colossal objects could form so early in cosmic history. These refinements also impact the study of relativistic jets, powerful, collimated outflows of plasma launched from near the black hole's event horizon. Understanding how such jets form, remain coherent over vast distances, and interact with the surrounding medium remains one of astrophysics' enduring challenges. Thanks to its energetic jet activity and dense environment, this quasar offers unmatched data for testing theoretical models of jet production, collimation, and magnetic field dynamics. Moreover, it provides a benchmark for calibrating black hole diagnostics. Emission line regions around the quasar help refine methods used to estimate black hole masses, accretion rates, and spin, enabling more accurate interpretations of active galactic nuclei across cosmic time. These calibrations are essential for population studies exploring how black holes evolve statistically across billions of years. Forthcoming spectroscopic surveys by missions such as Euclid and the Nancy Grace Roman Space Telescope will dramatically expand the catalog of quasars in dense environments. These large datasets will allow astronomers to place rare systems like this one in proper statistical context, identifying how common such evolutionary pathways are and clarifying the diversity of feedback mechanisms in different galactic environments. In terms of galactic growth, the quasar also informs our understanding of mergers, key events that drive mass assembly, morphological change, and black hole fueling. Many luminous quasars are thought to be the aftermath of major mergers. Studying the structure, dynamics, and star formation properties of this quasar's host galaxy and its neighbors allows researchers to trace how such collisions reshape both galaxies and their central black holes. The object's influence extends into dark matter research as well. Gravitational lensing caused by its host galaxy cluster enables astronomers to map dark matter distribution with high precision. Subtle distortions in the background light can reveal the presence of smaller dark matter clumps, helping constrain theoretical models about the nature and behavior of this elusive component of the universe. Astroinformatics, where astronomy meets advanced data science, also benefits from the wealth of data this system provides. Its multi-wavelength observations are ideal for training machine learning models, testing new classification algorithms, and refining statistical methods. Through such work, researchers can automate quasar detection, identify anomalies, and model variability patterns across vast survey datasets, helping to accelerate discovery in the data-rich era of modern astronomy. Beyond science, this cosmic giant invites philosophical reflection. Its scale and power challenge our perceptions of time, matter, and existence, highlighting how deeply interconnected cosmic processes are. Studying such phenomena not only satisfies scientific curiosity but also touches on questions of meaning, reality, and our place within a vast, evolving universe. Educationally, this object serves as an inspirational gateway to STEM disciplines. It exemplifies fundamental physical laws, gravity, light, thermodynamics, while offering dramatic visual and narrative tools for outreach. Through public lectures, documentaries, and interactive media, this quasar becomes a powerful vehicle for engaging minds and inspiring future scientists. Its exploration will also be enhanced by next-generation facilities. Missions like Lynx, Athena, JWST, SKA, and massive ground-based observatories will provide sharper images, deeper spectra, and more detailed environmental data than ever before. These tools will help refine our models of black hole accretion, feedback, jet behavior, and galaxy formation at unprecedented scales. Ultimately, continued study of this extraordinary quasar promises to shape progress across astrophysics, cosmology, plasma physics, dark matter theory, and data science. Each new insight brings us closer to understanding the deep structure of the universe, from black holes and galaxies to fundamental matter and energy. As humanity looks further into space and deeper into time, rare objects like this one guide our search for truth, reminding us that the universe is as mysterious as it is magnificent, and that our desire to understand it is limitless. As we push further into the era of precision cosmology and ultra-deep surveys, this extraordinary quasar stands as a sentinel, a cosmic monument bearing the signatures of extreme gravitational and energetic phenomena that have shaped the large-scale structure of the universe over billions of years. It is not merely a luminous object, it embodies the transformative power of black holes and serves as a natural laboratory for probing cosmic feedback, cluster evolution, and the interconnected architecture of matter and energy across time. One of the most promising frontiers in its study lies in integral field spectroscopy, IFS, which enables astronomers to construct detailed three-dimensional maps of gas, dust, and stars in the surrounding environment. Instruments like MUSE on the Very Large Telescope, and future IFS systems aboard the 30-meter telescope or the Extremely Large Telescope, will resolve complex kinematic structures near the quasar's core. These high-fidelity maps will expose shock fronts, ionization cones, turbulence zones, and filamentary inflows, offering a dynamic picture of how material flows toward and away from the central black hole. Understanding these inflow-outflow processes is central to resolving a long-standing paradox: how such massive black holes grow rapidly while releasing enough energy to disrupt their own accretion. Simultaneously, this system offers insight into the enigmatic cool core phenomenon in galaxy clusters. Many clusters exhibit central regions where the hot intercluster medium loses energy through X-ray emission, theoretically enabling gas to cool and collapse into new stars. However, in the presence of powerful AGN, this cooling is often arrested, suggesting a finely tuned feedback loop that regulates not only star formation but the thermal balance of the entire cluster. Observations of this interplay offer critical constraints for simulations modeling AGN feedback and improve our understanding of baryonic physics within cosmological frameworks. The relativistic jets launched by this object further provide a pristine environment for studying magnetohydrodynamic instabilities and plasma reconnection, processes nearly impossible to replicate on Earth. Internal jet structures, knots, shocks, helices, can reveal key parameters such as black hole spin, magnetic field topology, and energy transport efficiency. High-resolution imaging at radio and millimeter wavelengths with facilities like ALMA and the Event Horizon Telescope promises to unveil these jets in extraordinary detail. As our observational capabilities advance, we may even approach the ability to resolve the black hole's immediate surroundings in such distant systems, mirroring achievements with M87* and SGR-A*. Beyond the central region, ultraviolet and X-ray photons emitted by the quasar illuminate vast volumes of the circumgalactic and intergalactic medium, producing extended emission line regions, ELRs. These ethereal structures trace previously invisible gas on megaparsec scales, acting like cosmic fog lit by distant flames. Mapping such emission provides key insights into the reach of quasar influence and the extent to which feedback can affect galaxy formation well beyond the confines of the host halo. As technology matures, this quasar will likely become a standard calibration target for space-based interferometers, X-ray polarimeters, and next-generation far-infrared observatories. Its brightness, contrast, and well-characterized structure make it ideal for testing instruments, refining distance indicators, and expanding observational frontiers. Each leap in instrumentation peels away layers of cosmic time, bringing us closer to understanding the earliest epochs of structure formation. The object also raises essential questions about the long-term fate of hyperluminous quasars. When their fuel is depleted, do they fade quietly into dormancy, leaving behind massive but inactive black holes? Or do they flare in episodic bursts, reigniting as fresh material becomes available? Fossil structures, radio lobes, X-ray cavities, and relic nebulae may contain the answers, revealing how long these giants exert influence after their peak activity ends. In this way, we begin to glimpse not only how the most powerful galaxies live, but how they die. More than a brilliant point of light, this quasar is a convergence point, where black hole physics, galaxy evolution, feedback mechanisms, large-scale structure, and cosmology intersect. It is a window into the extremes, a dynamic archive of the forces that sculpted the universe. Every photon it emits encodes a chapter of cosmic history, written in energy, magnetism, motion, and time, awaiting the tools, theories, and vision needed to fully decipher it.